In this experiment, we used a lot of equations to help us solve for maximum height and initial velocity. To find initial velocity, we knew that at the time of the apex would be 1/2 the total time. And also at the apex, the velocity is 0, so it gives you the equation velocity equals negative at. Once we solve for v, which in this equation is the final vertical velocity, we also know the initial vertical velocity because the two equal each other, as we have previously proved. Once we know that, to find the maximum height, we use the equation the initial velocity squared times sine squared theta, and theta is the angle in which we launched our rocket, and all of that over 2 times gravity. Another method we can use to find the initial velocity is the equation delta x equals the initial velocity squared times sine of 2 theta over g. Using that, we can derive the equation that the initial vertical velocity would be the square root of g times delta x over sine 2 theta. We can easily find delta x because that would be measured with our tape measure, and the theta in this equation is our launch angle. We must also acknowledge that the rocket is not starting from the flat bottom, but it is starting from with a little elevation because of the launcher. In order to keep this experiment as reliable as possible, we had Gabe stand with his back as straight as possible and his arms extended as far down as they go, holding the college physics textbook. In terms of the wind blowing at a constant speed versus a constant acceleration, we know that the wind was blowing at a constant speed because the wind wasn't tampering with our experiments in any notice display. We also know that the wind from 11:58 to 12:14 was blowing at an average of 1.25 meters per second. Let's talk about the optimum launch angle. The optimum launch angle is 45 degrees. This is known because 45 degrees allows for maximum time in air with the highest horizontal velocity. We did 4 experiments, and the angle at which maximum range was achieved is at 16 degrees, because for us, that's when the rocket traveled the farthest at 4 meters and 24 centimeters. In order to calculate the percent difference, we had our angle in which maximum range was achieved, which was 16 degrees, over the optimal launch angle, which was 45, multiplied by 100, and that gave us a 36% difference. We know that the wind in this experiment was headed north, as we will prove later. So in terms of air resistance, we know that there was a lot of horizontal wind, and this made the lower the launch angle, the more north horizontal velocity was there. And this combined with the high horizontal north wind speed meant that the rockets also gained velocity when they traveled north. This makes sense with our angle at which maximum range was achieved, which was 16 degrees. Because the angle was launched closer to the ground, it picked up more horizontal wind and made it land farther. We launched our rocket 4 different times. The first one was from an angle of 45 degrees. It took a total of 1.00 seconds and traveled 3 meters and 74 centimeters. The second rocket was launched from an angle of 73 degrees. It took 0.96 seconds and traveled 2 meters and 48 centimeters. The next rocket was launched from an angle of 16 degrees. It took 1.01 seconds to travel 4 meters and 24 centimeters. Our final rocket was launched from an angle of 59 degrees. In 1.06 seconds, it traveled 2 meters and 77 centimeters. Which way is the wind blowing, Professor Gabe?
Blowing this way because it's north.
Ah! Is this way north?
Yes, this way is
North!
north.
North. And we know this way's east because this is the way we pray. From 11:58 to 12:14, we found that the average wind speed was 1.25 meters per second. North. We also launched our rockets north, meaning that the wind would push the rockets more. We found the average wind speed at the time of our experiments, and the direction was done using a compass, as seen in the video. Additionally, if there was significant updraft or downdraft, the data would be skewed. Most importantly, the maximum height would have been affected. The rockets would take longer or shorter to fall, depending on the amount of updraft and downdraft. Now it's time for the math. We're using theta to be 45 degrees and at a time of 1.00 seconds. We know that at the top of the time of the apex is 0.50 seconds, since that's half of 1.00, and then we have that the velocity equals negative 9.81, which makes it positive. So it's 9.81 times 0.5, which is 4.905 meters per second, and that's the initial velocity, the initial vertical velocity. Now, to find the maximum height, we just plug that into the equation we found earlier, which is, so it'd be 4.905 squared times sine squared of 45, and all of that over 2 times 9.81, which equals 0.61 meters. It is important to acknowledge that this equation does not account for any air resistance, including updraft or downdraft, which, as mentioned before, will significantly affect the maximum height. On October 6, 2021, from 11:58 to 12:14 at the Goodman soccer field, there were fair conditions. We already proved that the wind was traveling north using the compass, but now we will prove that it was traveling at about less than 2 meters per second. If you look at Gabe's hair, you can't really see anything, but when you look at my hair, you see that my hair isn't really blowing. I would say about less than 2 meters per second. We found that with no wind, the rocket, launched from an angle of 45 degrees, should have traveled 2 meters and 45 centimeters. However, in reality, it traveled 3 meters and 74 centimeters. This proved that the wind in this scenario was about 1.29 meters per second. We did it again and found that the rocket should have traveled 1.26 meters, but in reality it traveled 2.48 meters, which meant the wind went about 1.22 meters per second. Since the time of this experiment was about 0.96 seconds, you have to give or take. This will give us an average of 1.25 meters per second, while also acknowledging the delayed human reaction time. While we only did our experiment in one day, so the conditions didn't change that much, the wind is completely unpredictable and changes every second. 1 second, you're watching Chiefs-Bills Sunday Night Football, and the next second, it's a windstorm watch. The average Stomp rocket has low mass and low surface area. It is also very dynamic and has standard fins, which all contribute to the air drag. It was also traveling at the slow rate of 2 meters per second. When we launched this rocket out of the launcher, it traveled straight, but on the way down it dilly-dallied thanks to the wind. In our calculations, we assumed that the rocket was in free fall throughout its entire journey. We know that this isn't true because we proved that there was wind. However, there wasn't a significant amount of wind, so our calculations are sort of justified.